Have you ever seen one of those massive container ships and just wondered about its shape? I mean, why in the world is the bottom so incredibly flat? It almost seems wrong, But it's actually one of the most brilliant design choices in all of modern shipping. And today, we're going to solve that puzzle. Okay, so let's just dive right in. Picture this. On one side, you've got a sleek sailing yacht. It's got that deep, sharp keel that just slices through the water. And on the other side, a colossal cargo ship that honestly looks more like a giant floating bathtub. The difference couldn't be more obvious. And that really gets to the heart of it, doesn't it? That deep keel just makes intuitive sense for stability. It's like a heavy weight at the bottom that keeps the whole thing from tipping over. So why would the ships carrying literally billions of dollars of cargo use a design that, at first glance, looks like it's just asking to capsize? To figure out the flat bottom, we first have to really get a handle on the deep keel. And it all comes down to a concept called weight stability, which is basically a constant tug of war between two different forces. Okay, first up is gravity. Pretty straightforward. The center of gravity is just the point where you can imagine all the ship's weight is concentrated. So by packing a ton of heavy stuff like lead way down low in that keel, you're basically dragging the ship's center of gravity as low as it can possibly go. Now the other force is pushing up from the water. That's buoyancy. And the center of buoyancy is the central point of all that upward push. Since most of the ship's volume, the part pushing water out of the way, is in the main hull up near the surface, this point is naturally a lot higher than the center of gravity. So you've got this upward push that's high and a downward pull that's low, and this creates what you can think of as a dangling effect. It's like a pendulum. Anytime the ship tries to lean, that low, heavy center of gravity is always trying to pull it back upright. It's a constant correcting force. And the principle behind it is just incredibly powerful and simple. As one expert puts it, if you can keep that center of gravity below the center of buoyancy, it's pretty much impossible to flip the boat. That's weight stability in a nutshell. But here's the catch. There's always a catch, right? This beautifully simple solution has one enormous drawback, especially when your main job isn't just sailing around, but carrying massive amounts of stuff. This is the question that changes everything for ship designers. I mean, a yacht carries a few people. A cargo ship needs to carry thousands and thousands of tons of goods. Where are you supposed to put all that extra weight? Let's just walk through it. An empty ship with a keel? Super stable, no problem. But then you start loading it. You fill the hold, and then you start stacking containers higher and higher and higher on the deck. All that weight up high raises the ship's overall center of gravity. And as that CG gets higher, that righting force we talked about gets weaker and weaker until the ship becomes dangerously unstable. So you see the problem. Weight stability actually fights against cargo capacity. To solve this, engineers had to think outside the box, or in this case, outside the keel. They had to look for inspiration from a much older and honestly a far cleverer design. And that inspiration is the outrigger canoe. Now I know what you're thinking. A canoe? What does that have to do with a giant cargo ship? Well, it turns out the physics behind this ancient boat holds the key to this entire mystery. Now get this. The outrigger canoe completely flips our last rule on its head. Its center of gravity is actually above its center of buoyancy. Yeah, according to the logic of weight stability, that thing should just roll over instantly, but it doesn't. And the secret has nothing to do with weight. It's all about the shape. Here it is. This is the aha moment. When the canoe starts to lean, that outrigger arm digs into the water. This suddenly adds a huge amount of buoyancy way out to the side. The overall center of buoyancy instantly shifts outward, creating this massive lever that just shoves the canoe back upright. You see? The stability comes from the movement of the buoyancy, not the fixed position of the weight. And that, my friends, is what engineers call form stability. It's stability that you get purely from the shape, the form of the vessel. This lets you have a much higher center of gravity, which means you have a lot more room to stack cargo up high. So, how does this get us back to our cargo ship? Well, that big, wide, flat bottom acts like a built-in outrigger on both sides of the ship. The moment the ship starts to lean, one side of that wide hull submerges deeper into the water, the center of buoyancy shifts way out to that side, and that creates the exact same powerful righting force we saw in the canoe. Now, the technical term for this is the metacenter. You can just think of it as the pivot point for that shifting force of buoyancy. A really wide hull creates a very, very high metacenter. So as long as you keep your ship's center of gravity, even when it's totally loaded with cargo, below that high pivot point, form stability is going to keep you upright. Okay, let's bring it all together. We have two totally different ways to keep a ship stable. So how does a shipping company decide which one to use? Well, as with so many things in our world, it all comes down to the bottom line. This chart just lays it out perfectly. You've got weight stability on one side. It's simple, it's inherently super safe, but it eats up valuable space and weight. Then you've got form stability. It's more complex, you have to be really careful with your calculations, but the payoff is a massive, massive increase in how much you can carry. It really just boils down to a fundamental business decision. It's a trade-off. Every ton of steel or lead you dedicate to a heavy keel is a ton you can't use for paying customers. So what's going to earn you more money? The weight that keeps you stable or the weight you get paid to transport? And there's our answer. Modern cargo ships have flat bottoms because that shape gives them stability through form, not through weight. And this lets them safely carry the absolute maximum amount of cargo possible, turning that giant boxy shape into a floating engine for the global economy. So we've seen that a ship's shape is this incredible balancing act between physics and economics. And it makes you wonder, doesn't it, as you look at the world around you, at cars, at airplanes, at skyscrapers, what other brilliant engineering trade-offs are hiding right there in plain sight?